Guys, let's talk about hydraulic jumps. So hydraulic jumps occur when flow transitions from supercritical to subcritical. And here we've got a diagram of that. We have an approach flow, and it's under supercritical flow conditions. So it's flowing fast and shallow. And say we have a change in slope moving downstream, or we simply have a condition that creates supercritical flow, and then that flow might last for a little bit of time. It's really hard to maintain supercritical flow conditions in the field for very long distances. At some point, there's going to be a disturbance. Maybe it's a boulder, maybe it's actually an energy dissipation structure that was installed specifically to create a hydraulic jump, often downstream of spillways or dams or something like that. And so this hydraulic jump occurs, we get turbulence, white water, and that turbulence dissipates energy. And so we lose energy. We end up with a different energy. So we're thinking about specific energy. We end up with a smaller specific energy, a greater depth, a slower velocity downstream. Now, why do we have hydraulic jumps? Well, if you've watched that video from Practical Engineering, there's a lot of reasons why we want to have hydraulic jumps occur, and that is to dissipate energy, typically to reduce scour downstream of some structure, be it a culvert, a spillway, dam, downstream of any sort of water outlet. We don't want to have a lot of scour so we don't undermine the infrastructure in the river channel. So we create hydraulic jumps to reduce the energy of the water that's moving fast. So the challenge is often we're interested in understanding what the sequent depth will be, and that's the depth downstream of the hydraulic jump relative to the approach depth. So if we know the approach depth and we know the velocity of that flow, we can actually calculate this downstream depth using conservation of momentum. And if we write the specific energy equation for point 1, we have V1 squared over 2g plus the depth at point 1. And that's going to equal to the velocity squared over 2g at point 2 plus the depth plus some delta E. We don't know what delta E is. That's one of our challenges. So we lost energy. And because we lost energy, we don't lose momentum though. And so we can look at the conservation of momentum. Momentum is conserved. And the conservation of momentum equation then can help us, the second law of motion can help us then calculate this sequent depth. And to write this out in terms of a hydraulic jump, we have the sum of forces acting in the x direction is going to be equal to the momentum flux through the control surface. And here our control surface is the boundaries upstream and downstream of the hydraulic jump. That's our control volume. And here's our control surfaces. Okay, so if we look at the forces in this, we have the force, the hydrostatic force working as a kind of a force wedge or triangle on the upstream side of the hydraulic jump. And then we have a force wedge or triangle working on the downstream of the hydraulic jump. We're going to neglect the force of friction because we're going to assume that most of the energy lost, the majority of the energy lost to this is occurring due to turbulence in that hydraulic jump. We've got a normal force from the bed of the river. We have the weight of the water. And these two, of course, are canceling each other out. So we can write our equation as the sum of forces is equal to the discharge times the difference in velocities, the flux of water moving through those control surfaces. Okay, we can go back to our continuity equation. Velocity at point 1 times the area, cross-sectional area at point 1 is going to equal to the velocity at point 2 plus the cross-sectional area at point 2. We're not losing any flow here, right? We're losing energy, we're not losing momentum, and we're not losing discharge. And so for rectangular channel, we can make area as the depth times the width. So B is going to be the width of the channel. And we're going to assume that stays the same between these 2 points. And then we can create a relationship between the velocities. So velocity 2 should equal velocity 1 times the ratio of those flow depths, assuming that depth stays the same. We can also calculate the force, these 2 different forces. So that's going to be gamma H times area. So gamma H is equal to the hydrostatic pressure. We multiply that by the area, we get pressure times area, it gives us a force. And we know that that force acts at the centroid, which is going to be, for a rectangle, just halfway down. So that's going to be gamma times the depth over 2, and then times our area, which is depth times B. And so we end up with the force is equaling to 1/2 rho g, which is also gamma, times the width times the depth squared. And the same goes for the force in the downstream end, where we have the depth squared for the downstream depth. Okay, now back to our conservation of momentum equation. We can do this big derivation. I will scan these notes and you're welcome to follow along with us. It's a bunch of algebra, a little bit mind numbing. The fun thing is you end up using the quadratic formula to solve this equation. Ultimately, what we're interested in, though, is starting with the conservation of linear momentum, we end up with a relationship between the ratio of the depths and the Froude number. And if you recall, the Froude number is equal to the velocity of the flow divided by the square root of gravity times depth. So that's Froude number is going to be greater than 1 in the upstream direction at the supercritical flow, right? So Froude number is equal to 1 at critical flow. It's going to be greater than 1 for supercritical flow, and it's going to be less than 1 for subcritical flow. So this Froude number is going to be the Froude number for the upstream flow. And if we know the velocity and the depth, we can calculate that Froude number. So ultimately, we end up with this equation. And what it tells us is if we know either y1 or y2, or we want to calculate y1 or y2, and we know the Froude number for the approach flow, we can calculate this other y value. So typically, we're interested in what the sequent depth is, which would be y2. And so we can say y2 is equal to y1 over 2 times the square root of 1 plus 8 Froude number. I'll call that 1 squared because it's in the upstream direction, minus 1. So this equation then relates, again, the upstream flow depth, the upstream flow velocity, and Froude number to the downstream depth using conservation of momentum and all this fun algebra. A little bit of, I think there's a little bit of calculus in there too. Or maybe it's just, yeah, it's just the quadratic formula. So that's the equation that we're interested in at this stage of the game. You can actually calculate head loss now that you know the 2 different flow depths, because we can say flow depth 1 plus velocity head is equal to flow depth 2 plus velocity head plus the head loss. And that's the head loss due to the hydraulic jump. So you can go back and calculate that, and that's what this equation is right here. Head loss is going to be equal to the difference of those flow depths to the 3rd power divided by 4 times the product of those 2 flow depths. Another interesting thing to know, and that might be helpful to understand then what energy you've dissipated and what energy might be available to erode sediment downstream of a spillway or something like that. So this is a classic FE problem. That's why we're making sure we cover it here. There's obviously more nuance and things that happen with hydraulic jumps, and we can actually figure out how to design energy dissipators downstream of spillways to result in a certain amount of head loss from the hydraulic jump, as well as control what that downstream flow depth is going to be, which could have important consequences for infrastructure. Thanks for your attention, and thanks for learning about hydraulic jumps.